What's good, everybody? Welcome to a video on aerobic respiration. Now, this is an important video to set a foundation for a lot of different drug mechanisms, particularly metformin, as well as gain an understanding of how the body produces ATP, which is the primary molecule used to jumpstart reactions and create kind of energy. And so aerobic respiration is kind of broken down into a few different processes that you see here, including glycolysis, the Krebs cycle, and the electron transport chain. I'd like to point out that glycolysis takes place in the cytosol of a cell. So just imagine the blue box is a square, like this blue square is the cell. And then within that cell, there's a bunch of mitochondria. And so this whole aerobic respiration process starts out in the cytosol of the cell, and the products of glycolysis will move into the matrix of the mitochondria to the Krebs cycle, and then those products move to the electron transport chain, which ultimately creates ATP. Delving deeper into that, glycolysis is the first step, and it starts with a glucose molecule. So glucose is a molecule that you'll get from food that you eat. When sugar is broken down, this is the monomeric or smallest unit of sugar, and that glucose goes through a variety of different changes, as you can see on the right here, all of the different enzymes listed on the left and the things that are happening to that molecule on the right. And it goes through, as you can see, a variety of them. I don't want to go through all of them, but ultimately this process, glycolysis, will produce 2-pyruvate, 2-ATP, and 2-NADH. And so ATP we know as the molecule that creates energy for the cell, and NADH is a molecule that's really good at donating electrons so it can start other reactions, and will be used later on in some of the other processes. Furthermore, more pyruvate is what's going to be used in the next cycle. I also have some other fun facts about glycolysis just for biochemistry nerds out there. Moving on from glycolysis, before the pyruvate goes into the Krebs cycle, pyruvate has to be oxidized. In this process, you can see on the right here the different enzymes, once again in blue, and then the products that are created in red. And so you see the products are 2 carbon dioxide molecules, 2 NADH, and 2 acetyl-CoA, which is this kind of red molecule here. And the acetyl-CoA will go on to be used in the Krebs cycle, also called the citric acid cycle. So the acetyl coenzyme A will come in at this point here. It's marked as green, go through all of these different changes to produce all the products that you see on the left here. The primary products that we're interested in are the 6 NADH molecules, 2 FADH2 molecules, and the 2 GTP molecules, which become ATP. The ATP is obviously what we want to create from aerobic respiration overall, and then the NADH and the FADH2 will be used in the final process called the electron transport chain. Finally, after glycolysis in the Krebs cycle, we arrive at the most efficient cycle at producing ATP. And so the electron transport chain overall will take NADH and FADH2 that was produced in the prior cycles, and it will use that in a series of different reactions in these complexes to pump protons from inside the mitochondrial matrix to the inner membrane space to create a gradient, because things diffuse from areas where they're in high concentration to areas where there's a low concentration. So by using NADH and FADH to pump protons to this side, the inner membrane space, this creates a heavy gradient of protons on this side and forces them to want to diffuse back through. And when they diffuse back through, they have to go through this ATP synthase, and this ATP synthase ultimately changes shapes or conformations to catalyze ADP into ATP. And so we're going to go into even more specific details in a minute here, but just know that ultimately, after everything is said and done, there are 10 NAD plus molecules produced, which will go back to being used in glycolysis in the Krebs cycle, so that they can produce NADH and FADH2 for the electron transport chain, as well as there's some water molecules produced and 28 ATP molecules. So I did kind of a general overview of what's happening with the NADH and the proton pump, but this kind of just summarizes what I said. So as the electrons, if NADH here, as the electrons are donated into this first complex, the shape of these complexes change and pumps the proton to the inner membrane space. And then once again, because there's a high concentration of protons on this side of the membrane, it's going to want to diffuse to even things out, and it can only diffuse through the ATP synthase. And when the ATP synthase in blue here, when the protons flow through it, that once again catalyzes ADP into ATP. Now we're going to go into even more specifics about what the passing of electrons in those complexes looks like. And so going back to chemistry class, we have oil rig is the kind of mnemonic, and this means oxidation is loss and reduction is gain. And this is referring to electrons. So reducing something is when a molecule gives electrons to another molecule, and if a molecule is being oxidized, it's losing an electron. And so in the electron transport chain, NADH and FADH start off a long process of donating electrons. So you have NADH coming in here, donate 2 electrons to FMN. FMN donates to this iron sulfur complex, which donates to CoQ, which donates to cytochrome B, and so on and so forth. To get very technical about things, the reason that this flows so nicely from complex to complex is because each molecule has been perfectly placed in order of decreasing standard reduction potential. And so a negative standard reduction potential means that you're more likely to give up electrons, and a more positive standard reduction potential means that you want to gain electrons. And so if you notice looking at this table, it kind of goes down in order from the molecules that start the process to the molecule that ultimately ends the process, which is oxygen. And that's why you'll see that oxygen is commonly referred to as the final electron acceptor. So NADH starts it by donating an electron. It'll go through all of these all the way down to oxygen, which is ultimately used in creating that water product that we mentioned at the start of the electron transport chain video. Moving on to the next part of the electron transport chain, the final thing that catalyzes the changing of ADP into ATP is the ATP synthase. And so once again, the protons, I'll show you just briefly the image again. So when protons flow through the ATP synthase, this is the thing that will catalyze the reaction. Here, this diagram breaks it down into its different subunits and kind of just gives a different look at it. And so this cytosolic side is actually where the protons will come in. They'll come in here, change the conformation of this. This will turn, and then up here, these alpha and beta pairs will change conformation and kind of force the ADP and the phosphate together to create ATP. So in summary, ATP overall from aerobic respiration produces 32 ATP, 28 from the electron transport chain, 2 from glycolysis, 2 from the Krebs cycle. And then all of the 10 NAD plus goes back to fuel the glycolysis and the Krebs cycle so that you can continuously make more and more ATP. When you are playing sports or jogging or running, or you have just gotten really out of breath, you won't have enough oxygen to be able to use as the final electron acceptor. And so that's when you have anaerobic respiration. Instead of going through the whole process of glycolysis and the Krebs cycle and the electron transport chain, your body will just use glucose, go through glycolysis, take that pyruvate and turn it to lactic acid or lactate in order to regenerate NAD plus to be used in glycolysis. It's only producing 2 ATP at a time, much less efficient than the electron transport chain, but 2 ATP is better than no ATP. So if you don't have oxygen, this is what your body does. And that's when, they talk about lactic acid build up in your muscles and that sort of thing. Last, just some fun facts about the electron transport chain. Some of the most deadly kind of poisons, insecticides, and pesticides act on the electron transport chain. Cyanide acts by inhibiting complex 4, antimycin inhibits complex 3, and rotenone inhibits complex 1. Dinitrophenol, DNP, the most effective and dangerous fat burner, also acts directly on the electron transport chain. And that's actually what you see in this diagram here. Instead of the protons normally flowing through ATP synthase to produce ATP, When dinitrophenol is introduced into the human body, it very easily diffuses through all different types of membranes and barriers. It will actually get into the mitochondria, get into the inner membrane space, and it will bind up protons, and before they can go through the ATP synthase, and it will bring it across so that it can't be used to produce ATP. So your body ultimately is working really, really hard to pump these protons across, but these protons never actually get used to create the ATP and be properly utilized. So your body works even harder than normal. Really increases your body temperature, and you burn way more energy than you otherwise would. But obviously you can imagine this would be extremely dangerous and has led to some deaths, and is why it is actually banned. Furthermore, CoQ10, it's a supplement people at times often see, is a part of the different complexes in the electron transport chain. So if you go back, CoQ10 here is what passes electrons onto complex 3. And that's what you're taking in supplement form. Complex 2 is the only complex that doesn't pump protons. NADH is more efficient and yields more ATP per molecule than FADH2 does. Finally, one of the ways that they proved that this electron transport chain was how ATP was produced was they put bacteria in acidic media. So there's a bunch of protons floating around in the solution, and they were able to produce ATP even without the electron transport chain creating that proton gradient. So I hope this video has been informative, and have a good day.